At the core of everything we are doing with Makya is the simple idea. Generate optimized molecules, not just valid ones, not just novel ones, but molecules that matter. In this session, we'll show you how that's done. Not with generic AI models, but with design strategies that are rooted in chemistry, shaped by data, and guided by your goals as a scientist. Let's move from strategy in theory to strategy in practice, starting with case number 1. Here we're asking, how can protein and ligand structures guide the de novo molecule design? In this example, we are using Makya's strategy of growing from a fragment with one exit vector. So how does this actually work in practice? We start from structural information, a resolved protein ligand complex that gives us insight into which part of the molecules are making critical interaction and where there's room to grow. In this case, the referent compound is a known PIM1 inhibitor. We've identified a region of the molecule that we want to change and introduce novelty. Using Makya's fragment growing generator, we introduce diversity specifically in that region, expanding from a known binder into an unexplored space. This is targeted informed de novo design. You are not starting from scratch, you are starting from structure. Before the generators start proposing molecules, the first step is to define the chemical design space, and that control is entirely in the user's hands. We start with the initial fragment and a specific reactive center or exit vector where new chemistry can be introduced. This defines where Makya can start building. Then we apply substructural constraints, for example, filtering out PACE and TOX, using forbidden smart patterns. Again, this is all set by the user. We can also apply descriptors filters like limiting molecular waste. These are constraints that reflect your real-world project needs. Finally, Makya predicts compatible building blocks and reactions from a commercial datasets, ensuring what's proposed isn't just theoretically interesting, but also synthetically accessible. Once we define the chemical constraints, the next step is to guide the AI with a reward function to help it prioritize what good actually looks like. In this case, we are leveraging structure-based rewards. On the left, you see MDAT docking, which evaluates how well the generated molecules fit into the binding site. On the right, we take it a step further with fingerprint interaction scoring, a more detailed assessment on how well the molecule replicates or enhances key protein ligand contacts. Together, these two rewards turn Makya from a generator into a targeted optimizer, focusing exploration on molecules that are not only synthetically feasible but also biologically relevant. Now we are taking reward-guided generation even further by moving into Makya 3D. Here we can guide the AI to prioritize molecules that form specific, meaningful interactions with the protein. In this example, we are highlighting critical contacts with glutamic acid 121 and lysine 67 on the hinge and catalytic pocket, respectively. To do this, we use a proprietary score function developed at Ictus, the contact score. This score rewards molecules that reproduce or enhance these key interactions. You are telling Makya where to grow and why certain interactions matter. And because you define which contacts are important, you maintain full control over how biological relevance is baked in your design process. Now let's take a look at how all this comes together inside the Makya platform. Let's start by setting up the 3D structure-based generation environment. We head into the docking file section and we create a new setup. Here we choose our docking engine, either Bina or RDoc. In this case, I'm using RDoc since it's faster and supports water molecules, metal ions, and cofactors. Next, we upload the PDV of our protein and the SDF of our reference ligand. If you have water molecules that you want to dock using RDoc, then you can click Yes. So this way, Makya will use them during the docking process. Then you click Validate and you will be redirected into a page where you will observe your protein and your reference ligand. By clicking Save, Makya will start the preparation of your docking file. Here, there is important consideration. This is not a full protein preparation. Your protein structure needs to be pre-processed before uploading. Makya assumes you're working with a structure that's already ready for docking. What Makya does here is format and organize the files so they can be used by RDoc or Bina in the generation process. It's a technical prep, not a chemical one. Once the preparation of the docking files is completed, we move into the 3D structure base section. Here, we're going to create a new docking parameter. We're going to choose the engine for the docking and then the file that we want to work with. After that, we're going to be redirected into a place where you can observe all the non-covalent interactions between your reference ligand and the protein. As we mentioned before, we've identified two residues that are key for the binding and the activity, which are the glutamic acid 121 and the lysine 67. That's why I want to prioritize the generation with these key interactions. The way that we have to communicate to Makya that these residues are important is by flagging them with weights. The higher the weight, the most important the residue is. In this case, we are adding a high weight to both of the residues to flag the importance of both of them in the generated molecules. After that, we can click Save, and our 3D parameters, they're going to be completed. Let's now move into the generator setups in order to see how you can put together the settings for your chemical constraints and your reward functions as well. So the first step is in the exit vectors module. Here we decide the initial fragment, which is the bisphorophenyl, and the reactive center or exit vector, which is the boronic acid. Then, since we are working in a heat discovery project and we are exploring more horizontally, we don't want to add a lot of complexity to the project, we ask the generator to only work in two different steps. We, of course, added certain product constraints, for example, a maximum molecular weight of 650 and a QED minimum of 0.3. Also, we've added pains and togs in the forms of smart list in order to flag all those substructures that are problematic and that we don't want to see in our generated molecules. Then we need to link our 3D structure-based settings with the generators in order to be used as a reward during the optimization phase. So in this case, you will be able to choose from all the settings that you have and you may want to use. So one important consideration is that in order to be able to make it for being able to score your molecules, it needs an anchor. This anchor needs to be a substructure of your reference ligand and also needs to be part of all your generated molecules. This anchor acts as the alignment point so Makya can superimpose all the new compounds and calculate the contact score. If you don't have an anchor, then you cannot score your molecules. In this case, the bisphorophenyl fragments we started with is also our anchor. So now that we have all the settings for the chemical constraints, the reactivity constraints, and also the reward, we're going to move and see which molecules Makya proposed. In all of them, we see that we have the bisphorophenyl, and then Makya proposed different kind of diversity around this exit vector. If you click and see detail, now here you will see your initial fragment, your reactive center, and the building block that Makya predicted to react with it and give the final compound. So here you will have different scores, like for example, VINA score, contact score, but also the retrosynthesis one, which is going to tell you how synthesizable your molecule is. You'll also be able to observe your molecules in the protein pocket, docked either by BINA or RDoc, and you will be able to visualize all the interactions between your generated molecule and your protein.